The last several exercises were focused on vector operations in correlation and cosine similarity. Now we're going to switch to vector operations in filtering and feature detection. And you will see that time series filtering and also image filtering, although I discussed that in later chapters in the book, but all these methods of filtering and feature detection in time series and images are all based on vector operations, in particular, the dot product. Dot product is everywhere. It's all over the place. Okay, so what we are going to do here is create an edge detector. This is actually not so different from the image processing aspects involved in scanning your luggage when you enter the airport. So they're looking for metal, so they have cameras with particular wavelengths that will look for metal. But then they also have image processing algorithms that do edge detection, so they can easily find a knife or a gun or whatever they look for. I don't know. Okay, so we are going to create an edge detector. That means we need a signal to search through with edges, and also we need a kernel. So the kernel is very simple. It's just a negative number and then a positive number. So the kernel looks like this. I actually use different numbers here compared to what I wrote in the text, but that doesn't matter. Anything that goes from a negative number to a positive number will be an effective edge detector. Basically, this version just biases the edge detection towards detecting positive edges or increases relative to decreases. Okay, and here's our time series signal. So it's all minus ones. You can also have this be all zeros. That doesn't really matter. And then it just goes up at some point for, some number of time points. So this is called a plateau shaped signal. And then basically we run convolution of this kernel on this signal. That gives us this result. You can see that the gray stem, so the gray dots are zero everywhere. And when the edge goes up, we have a plus indication. And when it goes down, then we have a negative indication. So this is done by computing the sliding series of dot products between this kernel and this time series signal. So in a for loop, then you would compute the dot product between this vector, which is actually just two numbers, and these two numbers, and then these two numbers, and then these two numbers, and so on. So I hope that's all clear. I also, of course, provide an explanation here and as well in the text earlier in the chapter. So now I'll switch to Python and I will walk you through my solution. So here we have the kernel. You can see it's just defined by two numbers. It's a NumPy array. It's -1 to +1. And then we have the signal, which is all zeros. And then I set it to be 1 for, a third of in the middle. But this is all arbitrary. I encourage you to play around with all of this stuff. You can make this be -1s like what I had in the book. You can set this to be 3 or 10. You can change these numbers. None of this stuff affects the application of linear algebra concepts like the vector dot product in signal processing. Okay, so first we just create and plot these two. So here we see the kernel, here we see the signal, and now we run through convolution. So I'm calling this output a feature map because we are going to be detecting features in this time series. And when we use this kernel, the feature that we are detecting is these sharp edges. So this will be a plus feature, and this will be a minus feature. Okay, and here's where we implement the feature detection through the mechanism called convolution, which is really just a bunch of dot products organized in a for loop. So you can see we have the dot product with the kernel. It's always the same kernel. And then we have the signal, and we're just isolating little chunks of this signal. Okay, and then I plot the results. So pretty straightforward. In fact, like many of these exercises, especially early in the book, there's a lot more challenge to just visualizing and plotting the results, and doing the actual math, the linear algebra computations is actually pretty straightforward and doesn't require a lot of code. Okay, yeah, so again, there's the feature map is 0 here, these gray lines. The feature map is 0 because there are no edges. There's nothing to detect. And here we get a positive edge and a negative edge.